as you know, this topic is very simple. Very simple, meaning that that's just these let me give you the revision, because look, the maths is very simple, but there are very important embedded concept that they wants to go through it. That's what so let me recapture and refresh you with this list for 10 minutes, because look, the maths is very simple. I don't want to show you that putting that equation down and put these values into that one and show you in the calculator. So it's quite simple, this topic, but this topic has a very nice details. It has some physical meaning. So this is from the lectures, but don't worry about that. I think this is the equations that basically we have shown you, and I will show you in the standards as well. We are basically working in section number 13, and I will share with you the screens here, so making sure that it's not distracted over here. So if you come back here, this is the simplest equations that we're going to use: 0.5 k1 k2 k3 fsy db square root f c dash. And this is for the smart cookies. You know, yesterday I mentioned that someone wants to play smart with the standards and blame the standards. So the standards has put the catch meaning that they want to restrict something that I will tell you in a minute. So this is a very basic equations. What these equations gonna tell you? These equations basically tell you that if I it's basically not cells. Basically this LSYT. What is LSYT? Where is my bars? Okay, here. This LSYT is just telling me, provide me the enough grip, that goes into the concrete, that grip, the length, that grip, when you extend it, these portions will yield it. That says that develop the yield strength of the cell. So if I pull it, this should not pull out. Like this should not pull out. So you need to provide enough length that this point here will be yielded. That's the main goal of our this LSYT. So I hope you understand that. And there are some specific parameters that will help us to find this grip. Some are our friends meaning they are helpful. Some will be apply the penalties. Standards will apply the penalty if you do something that is don't like it. So that penalty will be some of these penalty meaning they need more length, right? And it will be costly if you need more length. But of course you can't avoid those lengths. You need to put it there. But we don't want to prove it too much that it will just going to overkill your design. So that is funny. So these are parameters that I would like to explain. So bond strength. Look, this is uncracked sections. Okay, if it is cracked, then there is a one figures also used that in lectures that will happen. So look, this bar, when these bars comes here, they will extend it, and when they extend it, it gets smaller. When it gets smaller, then the bond between, look, to work this concrete and steel together, we need to make sure that this friendship between the steel and concrete will be strong enough. It will not break. So if you extend the bar and if you reduce the diameter, then there is a gap between the steel and concrete, and then they will not gonna work together. So therefore these ribs are provided. So these ribs will provide the interlock between the concrete and the steel. So that's how they provide the bond between that. So basically bond is saying that if you have a, let's say, if you take a typical cross sections of this one and magnify it, and if you take the bending moment on the both sides, it will have a tension here and it will have a tension here. There are two different tensions because of course due to different bending moments your bar will experience different stresses, different forces. So this bond that's in the green color, that bond stress or bond force is equal to this extra, because it should be equilibrium. So this T would be cancelled with this one, this C would be cancelled with this one, but this extra T that needs to be go somewhere, right? Because it's in equilibrium, this is not in space. So that equilibrium, so that is the bond force that will make it this extra T equilibrium. So that is the bond. There are some equations just to bonds. And look, the plain bar, we don't use these plain bars in the real world. Okay, it's very bad. Very bad means you need the large development length, and sometimes you can't have this large development length. So we use this ribs one, like a mechanical interlock. The scientific word is mechanical interlock, meaning that you have these ribs that hold the concrete and provide the locking mechanism. So that's about those, and some force that's applied to that locking mechanism. Okay, that's very important. I think yesterday I talked about it, that when you have there are 2-3 things that standards wants you to not happens. So when you have these, so this first one, let's say this figure, first one, that is called splitting failure, horizontal splitting failures. When you put your bar very close to each other means next to each other, then these failures will occur. The splittings, you can see the concrete between the two bars will split. So when you provide the bar very close to each other, okay, so standards don't want you to put the bar very close to each other, so then this splitting will occur, and standards will going to give us some mathematical restrictions that will stopping us to put the bar close to each other. So that is the first thing that we want to stop them. Second one, that if you put the bar very close to the corner, in one of the corners, then you will have this corner splitting. You can see this kind of splitting that in the middle figures that you can see here, that will occur. And if you put your bars very close to the bottom edge or on the top edge, then this kind of vertical splitting will occur. So the standards will going to stop us, like there is a figure here that going to targeting this one, that this value standards wants you to stop using these values, so we prevent these kind of failures behavior. So that's one of the factors will going to help you. Oh, I talk about pull out test. You remember that yesterday, that you have a concrete cylinder and we put this bar in the concrete cylinder, and then you pull that bar, and you keep pulling, making sure that this bar don't come out from the concrete. That's the main goal. We don't want to pull this one out. You make sure that we provide enough length. Enough length means if you put only this much, meaning if you put only that much, means look here, you can experience that one. If I just hold the tiny bits of this one, look at these tiny bits with my fingers, it's not enough. I can easily pull it out. But if I provide more gripping like this, it is hard to pull, right? So you can see there is enough, so we can't pull it out. So that's what the standards wants you. It is just very logical in the real world. So you can just grip it and then try to. So the standards wants you to give you this, wants you to find this length, which is there represented by LSYT, in a way that this bar don't come out and you have yielding here. So that's what the splitting. So that's just explaining that. What else I need to talk about? I think these are all the details. Development length. Okay, that's the development length. Like if you have a cantilever beam, this black color one, you can see that, and there is a factors K1 that I like to talk with you, that one by one now. This one. Now let's talk about this first one, K1. The definition of K1 is given here. K1 can be taken either 1.3 and 1, two options. 1.3 and 1. 1.3 bad. Why bad? Because the standards wants you to apply 30% penalty. You need to provide more gripping. If it is 1, very good. But you can't avoid it in some circumstances, so you need to provide that one. So how do you distinguish between 1.3 and 1? So they written horizontal bar with more than 300 millimeter of concrete cast below the bar. So meaning that if your bar is sitting here on the top of the beam, and if you just measure from the bottom of the bar to the bottom edge, if this measurement is greater than 300 millimeters, you take K1 equal to 1.3. If this distance from the top to this from the surface of the Rio to the bottom edge, if it is less than 300 millimeters, you take K1 equal to 1. Simple. K1 is very easy peasy, either 1.3 or 1, depending on how much concrete sitting below the Rio. I hope it makes sense. In the reality, what the standards wants you to capture, that if you have cantilever, in cantilever, your tensile Rio is sitting on the top, right? If you think of cantilever, if it is bent, the top portions will be in tension. Concrete is very bad in tensions, therefore we put the Rio in the top of the top of this one. So look at this top of this one, that okay, so standards wants you to making sure that this is not good. This is not good, meaning that these bars from here can easily pull out because it's very severe here. You can see they develop very high stresses here. These bars wants to come out very easily. So standards wants you to stop doing that one. How the standard stopping you to do that one? The standards is very smart. It says that okay, if you have this cantilever, please put extra 30% your development length. That's what they said. If you have a cantilever, that is your concrete is sitting below, you put extra 30. If you have 100, you just have 130 in cantilever. If you have a simply supported beam, it's just one. Simply supported beam meaning your tensile Rio in the simply supported beam, tensile Rio is sitting, so you never have these kind of 300 millimeters greater because your cover would be 40 millimeters, 50 millimeters. So in that case, your K1 equal to 1. So I hope you understand what standards wants you to do. So in here at simply supported, you don't have this severe like a high stresses like you will experience here in cantilever. You can imagine that if you jump on here, if you are jumping on here, what would happen at this end? And if you are jumping, let's say here, what would happen here? This will be very severe. So you can easily pull it out here. So therefore you have K1 equal to 1.3 and K1 equal to 1 in that case. I hope it makes sense. K1, anyone come across with any practice in your career or anyone, you should be able to distinguish between K1 equal to 1.3 and K1 equal to 1. Unmute yourself or put in the chats if you don't understand this K1. It's quite simple, and I also give you the logic. You don't need to remember anything. The written here, I also explain you with the figures and also explain you how the cantilever beam and why they are applying it. And probably that's the first K1. Now second, let's talk about K2. Look, K1 and K3 are proportional to the LST, meaning that if this increase, this will increase. This one increase, this one increase. Like our goal is try to reduce this one. As an engineers, if you want to not increase the cost of your Rio, your aim is to reduce this one, but you don't want to reduce in a way that it will compromise the safety of your structures. So you want to reduce this one. That is our goal, meaning that you want to reduce this, you want to reduce this, you want to reduce this, but this one you want to increase because this is inversely proportional. If you increase this one, it will goes down. So that's our main goal. Because if you are working on the multi-story buildings and if you just increase extra bit of this reinforcement, you are talking about $500,000 extra cost for your steel Rio. So that is significant for that. So you just need to efficiently design your development. So I hope you understand K1. You don't have much option, 1.3 and 1. Now K2 is about the diameter, dB. 132 minus dB over 100. What is dB? What is dB meaning? Is a diameter of your Rio. So basically diameter of your Rio. So I think I put the notes there that if you, I think mathematically I prove that okay, K1, K3 done. Here you go. So if you use 20 millimeter dia, you get K2 1.12. And if you use 24 millimeter dia, you get 1.02. 1.02. So you reduce as you increase the dia, you increase the, if you increase the diameters, you're reducing the K2, right? That's what it's happening, right? So if you reduce your K2, you will increase your LSYT. So what does it mean? It means that the larger the bial diameters, larger the development length. So what happens here? So if you want to use 20 millimeters diameters, right? If you increase 20 to 24, you increase this one, right? So the larger the diameters, more grip you needed. You can think of this pen and comparison this one. I can easily grip it. Look, and I can hold. If you have these larger diameters, it's require larger length to grip it, right? It's required height. But if I have smaller diameters, I can easily grip it. So I need a smaller length. So the basically larger the diameters, you need larger lengths. Okay, so therefore this 132 dB 100, and dB is the diameter of your Rio bar. So that is K2. K3 is 1 take away 0.15 CD minus DB and DB. Now CD is basically coming from here. That CD is basically coming from here, minimum of A2, C1 and C. So it's basically standards wants you to making sure where your weak point is. Weak point means did you provide closer to each other? If you put close to each other, your splitting will start first here. If you put this bar close to this edge, then your splitting will occur first. And if you put this close here, your splitting will occur first. So they will want you to take the minimum of this distance of this distance of this distance. And please note, this A is not center to center distance. This A is distance from the edge of this bar to the edge of this bar. I hope you understand that. So that just the standards wants you to prevent not happen that splittings and any of these ones. So basically there is a very good catch here. Very good catch here, meaning you can make it this K3 equal to 1 by taking CD equal to DB. So if you put CD equal to DB, in that case your K3 equal to 1, and as I mentioned, K3 equal to 1 is just a smaller. So basically, but there is a catch here that you can't make your K3 smaller than 0.7, because sometimes someone might come back and say that okay, I will keep increasing this CD and try to reduce 0.5, 0.4, 0.3, because if you reduce this one, this will reduce. So it's good for us. But the standards wants to stop that one, that you can't just go more than less than 0.7 or greater than 1. So that's the one limit here that's put here. So K3, you understand. FSY, whatever the bar you use, you can go back to this table here, the material tables. I think in the section 3, generally we use these deform bars. Basically this is deform bar. This is a deform bar, right? With the ribs one, there is deform bars. Generally we use deform bar with the class ductility N. So this is the class ductility class, normal ductility, low ductility, and generally we use this 500 megapascals. Typically we use 500 megapascals bar yield strength. So that is 500 megapascals dB. You know, this is depth diameters, and this is K2. That is I already explained. Square root FC dash, like basically why they put the square root, because they just wants to making sure that we use concrete compressive strength, concrete tensile strength, not concrete compressive strength. If you remember tensile strength, generally they put the square root. I can show it to you. In here they put the square root there. They put the square root. Someone might say what happened to the 0.6? Probably they done some kind of calculation here to rid of that 0.6, but that square root basically coming from your tensile strength, not the because your length will be governed by the tensile. Your Rio that you are trying to find is for tensile Rio. It's not a compression Rio. So your concrete, that length, they are concrete on the tension sides, not on the compression side. This concrete surrounding that Rio is experiencing the tensile force, not the compression force. So therefore they just targeting this one. And probably these are simple. FSY K1 we already figured it out, and DB is the diameter of your bar. So I hope that theory would help. And let's now talk about these examples here. Look, the maths is very simple. So I will not go through this maths. So 750 350 T-beam support a 300 kilonewton concentrate load. Factor at a center at is 800 simply supported beam. Basically it says that okay, if you have a simply supported beam and then you put these 300 kilonewtons concentric load, and the distance between the support is 8 meter or 8,000 millimeters. Based on bending moment at midspan. So if I just want to do the bending moments like this, you can calculate M star here. Based on the midspan, 4 and 28 bars design moment capacity are provided. So you have look, this development length calculation comes after the bending and shear checks, meaning that we generally do the bending check first. This beam are governed by the bendings. Okay, if this beam will pass for the bending check for the strength purpose, then we go for shear. Shear is not that that problematic. The beam generally no need to redesign for the shear unless you have a very near the support conditions there is a high shear zone, but generally this beam generally need to be satisfied the bending one. When the bending is okay, shear is okay, just we go for the development length. So for that we already know these 4 and 28 bars that is coming from your bending checks for this design capacity. If the flexure capacity for the section that reinforced 2N bar is 325, so you have these 2 and 28 bars sitting at here, 2 bars at 325 kilonewtons, so somewhere you have 325 kilonewtons. So determining the development length of this and 28 bars. So basically they want to use these equations. Basically they want to use these equations and plug all these values and tell me the LSYTV for two different bars. Two different bars meaning one for 4 and 28 bars. So we need to do it two times. One for this bar and this another bar. FC dash is given 25, which is friendly here, easy. So we can straight away plug 25 here. That is we can use it. What else we given? Oh, cover is given, all sides, and R10 stirrups given. So cover is given, that will be useful. I'm watching here, make sure that I don't turn it off that mute. So therefore I activated that window here. So make sure I don't mute it. So I think what was that? Oh, cover will gonna help us here. C1 and C, that will going to help this cover, and this is 30 millimeters. So we have this 30. We will figure it out A. So we just need to plug here, but this one 30 straight away. That is for the cover. So I think that is, as I mentioned, maths is simple. Some students wants to see the old version because look, there is a 2009 versions. We have a solution from that. Not huge difference, but there are some difference between 2009 and 2018 versions. And there is a 2018 version sitting down below. Every 10 years they will revise the standards. When you're working probably 2030, we will have new versions and there are some changes there. So I think you know this concentric load and so on, that we just need to figure it out. The bending moment diagrams, we will draw it later. So let's try to put those details here. These equations here that I have written on the screen, these equations, that's I take it from here, close. That's I take it from here, copy it, K1, K2, FSY, dB, K2 square root FC dash greater than 0.0 FSY, K1 dB. So that's I copy it from there. Now let's crack one by one. Crack one by one meaning, let's say you have a K1. First, let's work out K1. Now what is K1? As I mentioned, K1 has two options. K1 has two options, either 1.3 and 1. 1.3 comes when your concrete below the Rio bar is greater than 300 mm. Basically, we follow these US, these US standards that we follow. Generally, this US will work on the feet, the 1 feet. This is 300 millimeters. They just wants to put on the rulers. So when your bar is sitting here, and they just wants to put the ruler here and make sure that if you have this 300 millimeters concrete down sitting below this Rio, then say that use K1 equal to 1.3. If you have just that much concrete less than like 30 millimeters, we have it up to, I think not 300, we have 30 millimeters. I think up to here we have concrete up to 30 millimeters here. So we have this, this is in centimeter. Yeah. So we have 30 millimeters cover here. So we're going to use K1 equal to 1 for 2 and 28 bars. I hope you understand that. Where is coming from? Because we have this. If you work it out, this one, that is, let me magnify that. This is 30 millimeters. So basically this is less than 300 millimeters. So therefore K1 equal to 1, easy. Okay, so that's 30 millimeters given here. All right, so that's pretty much K1 done, easy, not that hard. We don't receive the penalty. We don't receive penalty meaning this is penalty, 30% penalty. The standards wants you to apply if you have a more concrete down sitting down. So we don't have penalty. We are happy, not bad. Now K2 was again easy peasy. As I mentioned, the larger diameters, larger length you require, your dB is equal to 28. Where is the 28? You can come back here, and this designation here, that is sitting 28. Nicely 28. So we have 28. So we just plug the value and put in the calculator, and we can get this K2 value easily. So you have just these equations are taken from here, 132 dB over 100. So that's K2, and 132 take away 28 over 100, which is 1.04. I think extra 4, 1.04. So that is good, not bad, because this increase is not 1. I like it 1.04 because it's greater than, if it is just increase, this will reduce. So using the bar 28 larger diameters is good for us, that you can see this K2 1.04, not bad. Okay, look, when you're designing it, you just need to make sure you need to have engineering feelings as well. It's not about solving just examples with plugging the calculator. You stop and think, what is gonna happen? You don't want to increase this length like 10,000 millimeters or 100 meters. That's not possible. So you just stop and make sure that you don't, a calculator don't just give you 10.4. You just stop and think whether is it making common sense, or it is just logically happening, or in the reality or not. So that's what my suggestions. K3. Now the K3 is, come on, K3 is here. 1 take away 0.15 CD dB dB, and dB already 28 diameter of your bar. CD we need to figure it out. Now the CD, how we can figure it out? CD has this one, minimum of A by 2, C1 and C2. Please note, C1 is the distance from the face to the side, and this C is the distance from the down of this Rio to the bottom edge. So that is C. So that is 30-30. This is basically cover given in here. So 30-30 we plug, we can find A by 2. We can find distance A, and distance A represent the distance from the face of the Rio, from one Rio to the next Rio. Okay, just from next to each other. So that's, we can figure it out easily. So let's say you have 350. How I figure it out? You have, let's say, 350. Where 350 comes from? I basically work from here. So let me. So you have 350 here. So from here I know this is 30. Then you have, this is 10. This is 28. This is A. 28 A. 28 A. 28 10 30. So what I do, I just take 350 equal to this 30 plus this 10. Oh, sorry, this is this 10 plus this 28 plus A plus 28 plus A plus 28 plus A plus 28 plus 10 plus 30. I hope you got it. And then you just sum them up. This is 2 and 3A, divide by here 350. You can find A. I hope you understand that. You just put all the numbers in front of 350, and then you can figure it out, this small a. That's what I done here. You can see that 30. Then you have a 10. This is Pitman's. Then 28A, 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 10, 30. So you just put those details here. You can get these A equal to 52.7. So you just put this in the minimum one, that 52.7 divided by 2, 40. Why I get 40 here? Probably something is, I missed that. Probably 30. We just need to change 30. I'm not sure whether they will change the answer or not. I think I have typo. Please correct it. Here we're going to get 30 here. I think the answer will not gonna change, because you have 30 here, you have 30 here. This 26 will the winner, because we need the minimum. So still answer will not change. So 26.33. So what the standards wants to do? So among that meaning you have 30 here, but this one was 26.3 something. So your splitting will occur first here. Standards wants to stop that one. So your between C1, C and A, where it gonna split? This will split between this bar. Right, because you're not going to split here, it will not going to split here, it will split because a by 2 is not, that's the minimum, so it will split here. So that's what standards wants you to stop. You need to provide enough development length, then you don't have that splitting happens here. So that standards wants, so there is 26.3 if you choose. If you choose 30, then the splitting will occur. So that standards make sure that you don't have splitting. So therefore we have 26.33. You plug that value in the K3, like come on, K3 is 1, that is coming from these equations. K3 equal to 1.15 CD minus DB on DB, and you just plug that value. CD is 26.33. We just got it from here. Then you have diameter 28. K3 is 1.009. No good meaning we need to make this check that it should be between 1 and 0.7. It's just increasing above 0.1, 1.009. So we just change it back to this K3 equal to 1 because this 0.9 is just a little bit extra there. Standard don't want to do that. Now we have all the values that we want to do it. 0.5, I think these equations I am using it from here. This one. 0.5 K1 K3 FSY DB K2 square root FC dash. K1 0.5 K1 we found 1. Do you remember that K1 guys, that you have not enough, that is only 30 millimeters of concrete, not which is less than 300 millimeters, so it's 1. K3 is just 1, that is CD, that's 1 here, 1 here. K2, you remember this K2 diameter of your bars, K21 that we figure it out, 1.04. So we just put that 1.04 there. Square root 25, FC dash, yield strength 500, DB diameter 28, you get 1346 millimeters. Look, when you specify this one, your builders will not gonna just go and just specify measure 1346. It will not. The builder will just not gonna go and say that okay 1346 or something. This is just centimeter, so they will not just gonna go and just say that okay 1346 is just this one. You just need to rounding it off, okay, to just increase. Don't round down because that would be conservative. If you increase a little bit extra, that would be satisfactory. So just put 1350. For your exams, you just use this one. But when you step into your work, you might need to rounding up, not down. There is a one check though they need to make. That one check is this, that it should be greater than this one, 0.05 FSY K1 and DB. Let's quickly make that check. That 0.015 FSY 500 megapascals K11. We found that K1, you remember that 30 millimeters, and DB is equal to 28. So it's 812. So standards wants you to provide 812 regardless of your parameters. Some smart engineers may come back and make it this one of these parameters somehow 0. I'm not sure. They play something. They are smart. And he make it 0, then said I don't want to provide any development length. Why not? Standards want me to not blame the standards. So as I mentioned, standards play smart. They said, oh, don't worry. If you get 0, don't worry. You don't consider 0, put 812, 800 millimeters. But in our case, it's not required because our length is 1346. So I think I just want to put the one notes here that if you have 1346 millimeters and if you don't have enough length, let's say you don't have enough length to provide this 1346. In that case, you can cog it. Like you can divide this one.
Vipul, you're on mute again.
Vipul, you're on mute.
Sorry, thank you. I think this problem does not occur, but today something is happening. So here they say that okay, if you don't have enough room, you can just put this 180-degree hook and that hook will just going to look after this full LSTY if you just half it. So that's what that details. I think the second one that I just like to refer, that there is another one as well that we need to work out. They say that can you please also do the 2n28 development length for 2n28. We done 4n28, but we need to do the same thing for 2n28 like this bar. So for that we need to repeat the same procedures. Same procedures meaning let me see, where is it? There you go, 2n20 bars. So you have a K3. K1 is K1, K3 and CD, and this K3 is this one. So I think we need to use the K1 here, that K1 equal to 1.3, because the concrete down below is greater than 300 millimeters. So we can use K1 equal to 3. I can show it to you. That's 2n20 bars that we just want to design. So that is 0.5, K1 equal to 1.3, K3. I think we just work it out CD. Now because we have this distance are far away, you can figure it out A distance. I think you know now that you have this A distance here from this face to this face, you know 350, and you can figure it out this A distance, and that A distance would be this here 350, 40 times 220, so you have 240. So if you just take a 240 half, 107, 40, 40, so you have 40 millimeters down there. And K3, I think you know this one, all this one, K3 is 40, because CD 28 over 8, you have 0.9. So it's exactly the same procedures that you just need to work it out for this LSYTB for the top bars. Same procedure, there is not much difference there. Now there is a one thing that curtailments that I like to explain. The curtailments meaning, let me explain you this curtailments quickly in that one. So the curtailments that you want to make sure that curtailment happens is look this when you draw the they say that okay, if you have these bending moments, then your bending moments at 650, then you need to determine 325. So what happens here? The standards wants to recognize that okay, you have these 650 kilonewton meters maximum moment, but look, the moment here is not that big, so you don't need to provide the reinforcement that is you are providing it here. You can cut it off. Because in this region your bending moment is small, so you don't require that much reinforcement. So standards allow you to make the curtailments, meaning it's not need to extend, you can cut it off. So these examples wants you to tell us that where you going to cut off. If you want to say that 350 kilonewton per meters, then you can just figure it out this distance by taking the bending moments, let's say M here, M equal to this force 150 times X. Let's say this is the X distance. So M 325, that is given in our example, 325 equal to 150 X. So X equal to 325 over 150, you get 2160. Let's take a round number 2150. So the distance X 2150, where your bending moments will going to occur 325 kilonewton meters in your beams. That is the X distance. Now standards has these provisions. I think I can show it to you here, that where they talk about these provisions. If you go to the section 8 in the clause, I think yesterday we work on that one, that they just wants to 8.3.1. they say that not less than, means greater than 1/3 of total negative tensile row required support shall be extended a distance equal to overall depth cross sections D beyond the point of counter flexure. So you just need to provide extra D. You can't just stop it here. you can't just stop it here. You need to provide extra D. So therefore they have saying that okay, whatever your LSYT plus D and this distance is your Y. It's just basically 4000 take away this 215 is 18450. So between these two you take these 2580. So you don't need to stop it here where your 325 cutoff. You need to provide extra D. So that's what they mentions in the standards. So you need to terminate your bar like 4000 take away to 45 is 1428 1420. I think that's this one. Okay, this development length 12 dB that is sitting here in the standards. I just want to show you that if you have this positive moment tensor and provided admin part, you have this 12 dB with the cog, one half extended into simply supported length. So that's what it's happening. I think it's just this curtailment I can quickly show you in the book. I think everyone has access to this book through the library. It's available online. Let me, oh, there you go. So basically it says that, okay, the bending moment is very high here. So in that case, you can just provide extra 0.2 ln up to here for greater than 0.5 AST. You can cut it off here as well because your bending moment is reducing. Then 0.3 ln and you can provide this 0.5 LST in here. In this region, you can just cut it off just quarter of your total AST in this region. For the positive, you can provide the full here because you have maximum bending moment here. But as you go past here, you have very less bending moment. So you have provision of just reducing your bar by 50% and the both end from this length 0.1 ln. So that's just the curtailment that standards wants you to. So you can cut your bars basically along the sun. It is very expensive to provide all these 3 bars all the way to here. You don't need it that much bar. That's what they say because your bending moment diagrams would be showing something different. So I just want to stop here. I just talked too much, but